Dr. Rico here. This is a lecture from my course, System Dynamics. The syllabus link is in the description. When gravity ghosts you, okay, you're familiar with the experience. Just when you think you're getting along so well with a vertically oriented, translational, mechanical system, gravity stops answering your texts. In this lecture, I'll try to explain this common experience. It seems that sometimes the force of gravity matters, and other times it does not. Is gravity really Hamletic, an ambivalent vixen, or is there some way to understand this phenomenon? Consider the following example, contrived to shed some light on this. Often, when considering a spring K, we focus on the velocity Vk across it, i.e., the time derivative of the displacement xk. We effectively differentiate away the constant unstretched length L from xk. We can think of xk minus L as the stretch of the spring. In this exercise, we will attend closely to the details of this stretching. Consider the mechanical harmonic oscillator shown in figure Ghost.1. Here it is. We have a mass suspended by a spring from some fixed ceiling. We have a length of the spring. We have L being the unstretched length of the spring. And we have L tilde being the length of the spring when it is in static equilibrium, which of course depends also on the mass. We will look at these two cases in particular and try to figure out what's going on with gravity and when we might be able to ignore that gravity. The problem states, derive a single input-output ODE, ordinary differential equation, for the system in terms of xk, the total displacement across the spring. Let the constant L tilde be the stretched length of the spring when the system is in static equilibrium, just like we saw in the figure. Solve for L tilde in terms of the system parameters. Show that when we change ODE dependent variable from xk to xk tilde, where instead of subtracting out L, we subtract out L tilde, the length of the spring when it's in equilibrium, gravity ghosts us. Okay? So, let's check that out. For this example, there's a much shorter way to derive the system ODE than our usual approach, and we will use it here, the traditional free body diagram application of Newton's laws, shown in figure Ghost.2. So let's take a look at this free body diagram. Let's remember how we would often approach this in a system dynamics way. We would draw a linear graph of this situation. We would derive a state space model from that linear graph, and then we could transform that state space model into a transfer function and an input-output ordinary differential equation in terms of whichever output variable we chose. However, that's a long run for a short slide on this problem, so we're going to take a little bit of an easier tack and just look at a good old-fashioned sum of forces using Newton's second law. So, the free body diagram with positive down, as we used in the diagram above in the schematic, we have the mass, which has two forces applied to it. Okay, it has the spring force and the force of gravity, Fg. I'm using the convention here that every force is positive in the direction of the coordinate arrow. Of course, you could choose a different approach where you can draw arrows in any direction that you like and interpret the results based on the arrow that's drawn. This is just my preference. It's just a convention that I use when I do dynamics problems. So, if we apply Newton's second law, then what we get is a sum of forces, so Fg plus the other force here is Fk equals the mass times the acceleration. So the mass is m. The acceleration, in general, if x is the position of the mass, xm is the position of the mass, we could take the second time derivative of that to get us to acceleration. Now, we're interested in writing it in terms of xk, the coordinate that describes the position of the end of the spring relative to the top of the spring. So this is equivalent to mxk double dot. And of course, maybe you had forgotten, but this is a good time to remember that Newton's second law is a second order differential equation, okay? And we're seeing it as such here. Okay, so the forces, Fg and Fk, we can write them out. And so let's do that here. Fg, and now we have to get the sign right. So Fg is going to be the mass times the acceleration of gravity, as it always is. It's positive because we have drawn it down in the positive direction of the coordinate arrow. And that is, in fact, the direction that it acts, downward, right? Good old-fashioned gravity. Okay, and the other force is the force of the spring. So we know we're going to use Hooke's law. We're going to assume it's a linear spring with spring constant K. And let's write it out. We'll get the sign in a moment. K, the spring constant, times, it's going to be the stretch of the spring beyond its unstretched length, right? So it's going to be xk minus L, the unstretched length of the spring. Now, the question is the sign right? Okay, we've drawn it pointing down in the direction of our coordinate arrow. However, we know that if we stretch this beyond L, then we should actually have a spring force upward, right? We would see that the mass is being pulled up by the spring. Of course, it could suspend this mass. The spring could suspend the mass potentially. So it's going to pull upward as the mass pulls downward. So the sign on Fk is actually negative here. Good. So substituting in the forces into our Newton's second law, ODE, we'll just go ahead and plug these in up here, which gives us Fg becoming mg and plus Fk, but there's a negative sign on Fk, so we'll subtract k xk minus L, and that still equals mxk double dot, second time derivative of xk. Let's expand on this a little bit here. Let's move things around so that we've got a more standard looking ordinary differential equation with all the xk terms on the left hand side and all the terms that don't include xk on the right hand side. We get m xk double dot plus kxk equals mg plus kl. Of course, we can always multiply both sides by -1, as we do here, and we end up with this equality, which is an ODE that describes the dynamics of this problem in variable xk. Great. So we definitely have gravity hanging out here. The force of gravity is still showing up. It shows up as a forcing on this ordinary differential equation. All right, so the problem asked us to explore what happens at equilibrium. And in equilibrium, remember, the time derivatives of xk are going to be 0. And we defined L tilde to be what xk is in equilibrium. So we'll plug those into this expression here. And this term goes to 0. This term goes to k. So we have 0 plus k L tilde equals mg plus k L. Solving this for L tilde, simply dividing by k on both sides, we get that L tilde, we cancel this k here, so we get mg over k plus L. So L tilde, the length of the spring when it is in static equilibrium with a mass, is L, the unstretched length, plus some more. Okay, so it's longer, as we would expect. Let's move on to the suggested change of variable given in the problem, which was that x k tilde is equal to xk minus L tilde. This is the change of variable that was suggested. So let's see if that new xk tilde is going to affect how this ordinary differential equation looks. Let's go ahead and plug it in. Remember, we're plugging it in to this equation here. So xk equals xk tilde minus L, or pardon, plus L, if you solve this for xk. So xk equals xk tilde plus L. This is the substitution we're going to do. So we have x double dot is the second time derivative of xk, so we'll do d squared dt squared, the second time derivative of, now instead of xk, we're going to do xk tilde with our substitution here, plus L, and, oh, pardon, this is L tilde, right? Plus L tilde, plus k times xk tilde plus L tilde equals mg plus kl. Now we are going to realize that the second time derivative of L tilde is 0. It's just a constant, right? So we have mxk tilde double dot from the first term, tilde double dot, plus k xk tilde equals, we're going to subtract k L tilde from both sides, so we're going to have mg plus kl minus KL tilde. Let's go ahead and substitute in what L tilde is from our expression up here. Okay, so we'll just rewrite the right-hand side. mg plus KL minus K times mg over K plus L. Now, if we distribute this, we have a negative mg over K times K. K's cancel. You get a negative mg, which cancels this term out. So the mg's go away. And the other term is negative K times L, which makes these two terms go away. And we're left with 0 on the right-hand side. The differential equation in full then is mxk tilde double dot plus kxk tilde equals 0. Okay, this is another way of expressing our ODE with just a change of variable. Now, we have a ghosted gravity here. Gravity's gone, right? We wrote a differential equation that's completely valid to describe this system. It doesn't include the force of gravity explicitly at all. And I will contend that that is actually what goes on in other cases when we see gravity just disappear from a problem that is vertical and is in a gravitational field. So we might say, alas, poor ghost. We have seen now that the gravitational ghosting occurs when we change variables such that the displacement is relative to an equilibrium in the gravitational field. It is simply a change of datum or reference position of the displacement that cancels out the gravitational term. There's the rub. We call this the equilibrium requirement for a ghosting gravity. Okay? For this reason, those performing such analyses with a flourish of the hand declare vertical displacements relative to equilibrium, and poof, gravity disappears without explicit justification, for the details make cowards of us all. But there are situations in which this would be a fatal error, those for which there is no equilibrium. For instance, consider if the mass in our previous example was suspended from a damper instead of a spring. In this case, no equilibrium exists. It would just continue to ooze downward. Without going through the details, or at least recalling the equilibrium requirement, it can be easy to fool oneself into wrongly dismissing gravity. So we see Hamlet here considering the existential question, to ghost or not to ghost. That is the question. So I'll leave you with a little poem. Remember me, ghost would be, for I am thy father's spirit. If gravitied with thee flee, the equilibrium requirement. Okay, that's all I've got for you today. I hope you enjoyed it. I'll see you next time. Take care.